All right, Cam, I'll just let a few people come in. I can see them coming in. All right, everybody, welcome to Builders Declare Australia's 25th webinar, Understanding Thermal Modelling. My name is Hamish, one of the founding members of Builders Declare and soon to be Sustainable Builders Alliance, but we'll talk about that a little bit later. And I'm the Director of Sanctum Homes, and I'll be your host for this evening. In the spirit of reconciliation, we would like to acknowledge the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to elders past, present and emerging, and extend our respect to all Aboriginal and Torres Strait Islander people today. Today, we are joined by probably one of the smartest people I know, Mr. Cameron Munro from Passive Analytics. Cameron has a PhD in aircraft aerodynamics and has spent 15 years working as a consultant building transport models to predict transport demands around cities, and more recently as a passive house consultant modelling buildings' thermal performance. Cameron is a keen proponent of using computer models to help understand our world so we can make informed decisions based on good data. Today, Cameron will draw on his 15 years of experience to discuss the role of thermal modelling in designing healthy, comfortable and low-energy homes. He will cover the who, how, when and why thermal modelling can benefit your project, and look at the cost benefits, diminishing returns and times when modelling should be done so you can make informed decisions that enable you to build the highest performance home for the lowest cost. And I can personally absolutely talk to the benefit of modelling because that's what we do in pre-construction in our business. And I can also vouch for Cameron's credibility and his thorough approach, and also to put things into terms that even I can understand. Today's webinar is very appropriately brought to you by one of our platinum founding sponsors, ProClimate, who are the building envelope experts. ProClimate have a range of amazing products for all your weather tightness and air tightness needs, and include, but not limiting to, Extasana and Mento for your external building wraps, Intello, which is their internal air tightness membrane, and they have a range of quality accessories to ensure durable air tightness and weather tight systems. You can check out ProClimate's fantastic range at www.proclimate.com.au. You can get in contact via email, which is welcome@proclimate.com.au. You can also get in contact with them, 1-800-776-254. And you can also check out Daniel Jacobs' Insta account, aka Airboss Dan, at Airboss Dan, for a heap of tips and tricks to keep your building envelope weathertight and airtight. And also be sure to check out ProClimate Australia's Instagram page, which is at ProClimateAU. All right, let's kick off today's event. The information you're about to receive is based on the experience of the presenters and may not relate to your situation. If you'd like more specific advice, please get in contact with us via email. Today's webinar will be around the 30 to 40 minutes, and then we'll have plenty of time at the end to answer a whole bunch of questions. Definitely encouraging you to pop your questions in the chat down the bottom. I'm also going to try something a little bit different at the end during question time, and I'm actually going to try and unmute people if they want to ask Cameron a question in person. If it doesn't work, I do apologise, and I'll just ask Cameron the questions, but I'll try and figure it out as Cameron's presenting things. Anyway, Cameron, over to you, mate.
All right, thanks very much, Hamish, and good afternoon, everyone. All right, hold on to your socks because we're going to go through quite a bit here. Hopefully it makes some sense, but do jump in with questions at the end if need be. Okay, let me start off with a little rant because we all like a bit of a rant. Time and again, I get questions along these sorts of lines, and I'm sure many of you do likewise. Sort of blanket statements like, for example, that you don't need triple glazing in Melbourne, or that you don't need slab edge insulation or under slab insulation in Sydney or Perth, or there's no point putting more than some particular R value of insulation in your ceiling, whatever it may be. I'm sure many of you get these sort of questions too. And the answer I always think to these sorts of questions is, it depends, or I don't know, because it does depend on the project, the climate, the orientation, the glazing ratio, so many factors that come into play. And so we can't apply heuristics to this. You can't say that you always need triple glazing in climate Y, or that you always need to decouple your slab in climate Z. Now, it's certainly likely that far more likely that you're going to need triple glazing in Melbourne than you are in Sydney, or triple glazing even more so, say, if you're building on Cradle Mountain. But it doesn't mean that it's necessarily so. And moreover, it depends what you're trying to do. Are you trying to build to the passive house standard or something slightly less than that? Are you simply trying to avoid condensation on your windows? So it depends. As Hamish alluded to, I started off my career as an aerospace engineer, and it won't surprise you, and hopefully will pleasantly give you confidence when you fly to know that when you jump on a plane, there have been many, many hundreds of thousands, or in fact millions of hours spent designing all components of that aircraft across a range of disciplines, from aerodynamics to structures to aeroelasticity, controls, landing gear, engine design, and so on. And every single part of that aircraft has been simulated in a computer model, and lots of calculations have been undertaken to make sure the wings aren't going to fall off, and that when you take off, you're actually going to get up in the air at the end of the runway. So I think it's pretty self-evident that we need modeling in aircraft design. On the right, of course, we have a house. So what modeling do we do for houses? Well, of course, we would, as an architect or a client or a building designer, we get together and work out the general layout. How many rooms do you want? Where's the views? How much glass do we want? Where are we going to put the doors? And then you go to the structural engineer. You engage the energy consultant to get you an energy rating. You make sure you hit the compliance standard. Then you go and do your construction drawings, and you're away with construction. And what I want to suggest to you in this presentation is that we need to think about this process a little differently. And what I've really just tried to describe there is the classic ways which I see modelling done in the building industry seems to really be one of achieving compliance, the checkbox approach, where we do our design, we go and do our thermal modelling, which would be NATERS in the way we've got to do it for compliance, or BASICs in New South Wales, and then go through, make sure we hit those minimum standards that are required, and go through and build. What instead I'm suggesting we need to be doing is a far more iterative approach, where very early on during that design process, during the concept design stage, when we're looking at the form factor of the building, the orientation, the glazing, and everything else that comes into play, we should run a very early model, thermal model of the building, to get some sort of idea about how this building is going to perform. And that's critically important if you're looking at passive house, because it is such a stringent standard to try and achieve. But even if you're not trying to achieve passive house, there are very significant benefits of trying to do that modelling early on if what you're trying to achieve is some sort of high performance, comfortable, healthy dwelling. And perhaps that's even more true now than it has been in the past because of all the cost issues we have. By coming in early, by looking at things like the form factor, so the shape of the building, you can really have outsized impact on the requirements that you're going to have for things like insulation. So to come back to that question that we had before of, double, single, double, triple glazing, for example, in a cold climate like Melbourne, Canberra, or Hobart, if you can build to a really tight form factor, you may not need the triple glazing. You could go for double instead, and so save the client tens of thousands of dollars. So there's a really strong cost-benefit equation that comes in here of trying to do that modelling very early on. So model early, model often is the mantra that I try to push. So let me give you an example of the sorts of things we can do. Now, I'm obviously come at the world from the passive house side, but I'm not pushing passive house in this presentation. And you could do this, follow this process in exactly, presumably in a very similar way using any of the other energy tools like Energy Plus or any of the NatHERS-based softwares as well. But I'm going to use the passive house planning package, PHPP, just because that's what I'm familiar with and use all the time. So let's take a generic building. Here's a nice and simple rectangular box. I've got north to the bottom left of the screen. Let's assume maybe it's a corner block or something, so I don't have any adjoining dwellings to the north, which is kind of nice for my passive solar gains. I've got a garage out the back there and maybe a dwelling to the south side of the building behind us there. So here we are at the early concept design where we've got an initial sketch of what the client wants in terms of the building. Let's run a really quick model. And this model, I did this yesterday in a matter of hours. Now, obviously, it's got a lot of shortcomings because it's not a detailed model, but it should give an idea about the message I'm trying to send. Let's assume, for argument's sake, that this building is in Melbourne, and let's build it effectively to code. So slab straight on grade, there's no under slab insulation or slab edge insulation. Let's put R6 bats in the ceiling, a standard 90mm timber framed wall with R2.5 bats in the wall. Let's even go for single glazing, thermally unbroken aluminium frames. So pretty much the bare bottom. And let's make it a pretty standard level of air leakiness. So 15 ACH, which is the air change rate. If you're not familiar with that number, 15 is pretty typical for new builds in Australia. The passive house standard requires 0.6, so about 30 times tighter. But conceivably with a reasonable attention to detail, you can get well under 10 ACH and should really be able to achieve under 5 without an extreme level of difficulty. So we can build that model that I showed you on the previous page. We can put in those assemblies, so the standard R6 ceiling and R25 wall, and we come out with a number of the heating demand. So in passive house, we're targeting 20 degrees in winter as your temperature in all rooms 24/7, which is actually a different boundary condition to what you have in something like NatHERS. So these are not directly comparable, these calculations, with NatHERS, which is where a lot of our difficulties arise. But let's just accept that's what passive house requires. So in order to keep this building at 20 degrees all winter long, we need 127 kilowatt hours per metre squared per annum. So the units there are kilowatt hours energy. That's what we buy off the electricity grid. Per square metre is referring to the treated floor area of the building, so the size of the house, and A is for annum, or year. So if I want to convert that to get an idea of how much energy do I actually need to pay my electricity supplier to keep this house warm, the answer is pretty simple. 127 times my floor area, let's assume 170 square meters, so around 21,000 kilowatt hours per year. At the moment, electricity is about 30 cents a kilowatt hour, so that comes to about $6,500 a year to keep that house at 20 degrees, which is a bit of an ouch kind of a number. Now, that's based on resistive electric heating. So let's just assume, for argument's sake, we put an electric coil into that slab, which is a pretty horrid way of heating our building. An alternative is to use an electric heat pump, which is a fantastic bit of technology I'm sure most of us are familiar with. And if we assume a coefficient of performance of that heat pump of 3, which is pretty conservative, which means that we put 1 unit of electricity in, we get 3 units of heat out, then we effectively reduce that heating, the cost to heat this home by a factor of 3. So we come out at about $2,200 per year to keep the house warm. So that's our starting point. And now is when the fun starts. And this is where the iteration with the client, with the architect, you go back and forth testing any number of scenarios. So the easiest sort of scenarios, just to give you a feel, are testing simple things like, for example, in the first column here, the ceiling insulation. I've actually assumed in the default case R6, but let's assume we had R5 insulation, or we were wondering about de-speccing this building and saying, well, what if I engineered it backwards and went back to R5 instead, saved a few dollars on the insulation? What sort of impact would that have on the building heating demands? And the answer is in the first row here. So the heating demand saved per square meter. So if you recall back on the other slide, this building required about 126 kilowatt hours per square meter per annum to keep it 20 degrees. If we upgraded from R5 to R6, then you would save about 2 kilowatt hours. So 2 out of 126 is not very much, really. It's a little under 2%, which really reflects the fact that the rest of this building performs so poorly. Remember, it is single glazing, aluminium frames, and so on. So for that small heat saving, that equates to about 300 kilowatt hours a year. At 30 cents a kilowatt hour comes out at about $92 if you heat your house with electric resistive heating, or about $31 if you heat it with a heat pump. Now we can make a guesstimate as to the cost difference of R5 to R6 ceiling insulation, and I've assumed here, based on some pretty typical numbers, that it's going to cost us about $500 to upgrade from R5 to R6. So you can work out pretty quickly the simple payback of that insulation upgrade for the client. It's going to be about 5.6 years, or if it's a heat pump, around 17 years. Now, I'm not suggesting that these are definitive numbers, and the point is, and coming back to the first slide, it depends. Depends on your climate, depends on the building. But for this particular sample building, that's the sort of number we're seeing. Now, the other thing I would point out is that I'm not so interested in the absolutes here, but rather the comparison, the trade-off between different options, because the other option I might consider is upgrading the wall insulation from R2.5 to R2.7. And I can very quickly test that in the model. We get a heat demand saved of about 0.4 kilowatt hours. And in terms of energy, the cost saving, that's about $20 a year through direct resistive, or about $7 a year with a heat pump, so not much. But the insulation cost difference, the upfront cost, is quite large, about $1,000. So straight away you can see that it's going to take you many more years to get the payback. So in terms of making a decision, a trade-off between which of these two would I do, clearly the benefit here sways towards upgrading the ceiling insulation over the wall insulation. And we could continue along those sort of line of thinking. So I'm just going to... But I would probably take a step back rather than jumping straight into potential solutions. Use the model to try and identify where the heat loss is. So we started off with a building with very large heating requirements, 126 kilowatt hours per square meter per annum. We can look at where the heat loss is occurring in the building. And this graph tries to illustrate that. And straight off, we see the red bit here is for the windows. So almost half of that heat loss is attributable to the windows. Remember, they are single glazed. About a quarter is through ventilation. So this is referring to the air infiltration and exfiltration. So the air coming in through leaky windows around all the junctions, and then disappearing up round downlights and so on up into the ceiling, and it's gone. And then another component is from the floor, because the floor was uninsulated. So those are let's target the low-hanging fruit. So we've identified the windows, the air infiltration, and the floors as our critical components of the building. So what can we do with those? So this is where we use the model to do those what-if analyses. We can't build the building 100 times and work out in practice which is the best thing to do, but we can use the model to do that, to provide us with the guidance, the insight into where the lower hanging fruit is. And so this graph is trying to illustrate that. So we're starting off on the left here with the red bar, which is our total heating demand for this building, about 127 kilowatt hours per square metre per annum. Let's identify the lower hanging fruit first, which was the windows. So what can we do to the windows? We could double glaze them. Now, they're still thermally unbroken aluminium frames, but just that act of double glazing those windows, and this is a sort of a moderate low-cost double glazing I've assumed here, will knock 30 kilowatt hours off that 127. So that's a pretty good chunk in one hit. Let's keep going. Now we could look at the aluminium windows. We know that thermally unbroken aluminium windows are an atrocious thing to put on buildings. But if I replace those with a thermally broken aluminium frame, I can reduce my heating demand by another 10 kilowatt hours. I can now go back to my glazing again. So in that first scenario, I've assumed a fairly modest double glazing. What if I go for a very high performance double glazing? And there's a big difference here. And this is the other little rant I have, is when people tell me, oh, I've got double glazing in my house, like, great, what have you got? Because there's a huge difference between the really cheap low-end double glazing and the highest performing double glazing, which really performs almost as well as the low-performing triple glazing. So there is a difference there. So again, we can get a really significant chunk improvement in going to high performance double glazing. So we knock off another 10 kilowatt hours. We could look at UPVC windows. So they will often be a little superior to at least your middle range or lower end thermally broken aluminium windows, knock off another 5. So already, just by treating the windows, we've close to halved the heating demand of our building. Now, the next thing that I'll look at is the slab or the ground. So we just had a standard raft slab. Let's start with the slab edge, because we know that the slab edge is the first place you would usually look to in terms of heat loss in trying to treat a slab. So with the 25, if I put 25 mil of extruded polystyrene insulation around the edge of my slab, the perimeter of my slab, I can knock off another 7 kilowatt hours. What if I instead were to go for 50 mil of XPS? Well, I get a little bit of an additional improvement, but for this particular building, it's not particularly significant. So already, without even having to go and call up suppliers to get pricing, we've got a fairly good guide here, I think, but it's probably not worth us for this building going to 50 mil slab edge. Then we can deal with the slab itself. So under the pads and even a fully decoupled slab design, if we put 25 mil of XPS on the slab, we get another really significant chunk off our heat demand. So another 14 kilowatt hours. If I double the thickness of that under slab insulation to 50, I knock off another 4. So again, significant, but you'll note the diminishing returns here. The first 25 mil of XPS knocked off 14. The second 25 mil only knocked off 4. So there is some optimum in terms of cost benefit here. Then the third category I alluded to before was the air infiltration or the ventilation side of the game. Now we started with assuming 15 air changes. If we instead go to 10, we can knock off 10 kilowatt hours, then halve that, another 10. We can then add a heat recovery ventilation system. We knock off some more. And then if we get really tight towards passive house levels, we can actually get below the passive house target. So you can see here is sort of trying to get us towards some sort of high performance number, and it doesn't necessarily have to be the passive house standard in terms of the thinking here, to get something that's the right cost benefit for the project. So what does that all mean in terms of running costs? Well, again, you can do the numbers. On the left here, I've got our starting case, and on the right, our passive house design. So with all of those treatments we had on the previous slide. What we get is a heating cost with a heat pump, and I'm assuming here we're using heat pumps, of reduction from around $2,200 a year in the code house to around $200 a year in the passive house. And we also get a halving in our cooling costs on the bottom there. But what is really interesting here is that in the code-built house, you're using 80% of your energy costs to heat the building, whereas in the passive house, you're actually using slightly over half to cool the building. So the balance between heating and cooling has changed. Now, that's largely because I've only addressed the heating demand side of the equation in this little optimization exercise, but it does reflect this sort of change in the trade-off that occurs. And this is really important, I think, when you try and couple it with solar generation, as we'll get to in a second. Now, the other thing just to point out is that the other benefit here, not only in terms of how much you have to pay for electricity, is of course you don't need as big a heating system anymore. And so here is the change in the heating loads. So this is the size, the capacity of the heating system that you need, with exactly the same scenarios that we ran before, and really a very similar trend. We're going from single to double glazing offers you a big benefit, as does each of the improvements in air tightness that we can make. And we end up with a setup that's actually around requiring for the whole house, so 170 square meters, around 2.8 kilowatts of heating load, which is tiny. It's a little over an air conditioner, a hairdryer. So that's a very much cheaper heating system than what was about probably 15 kilowatts that we were looking at with the code home. So let me just come back to this solar question. So this is about the balance between the heating demands in winter and the summer cooling demands. And the thing that I always try and reiterate is a kilowatt hour is a kilowatt hour. During the middle of July in Melbourne or Hobart or Canberra, it's probably overcast and gloomy. So no matter how big a solar system you have, you're not going to be able to self-generate the heating demands that you need. Whereas in the middle of summer, solar generation coincides very well with the cooling demands. So to me, the heating demands are more important than the cooling demands. Now, that's not to say that we shouldn't deal with summer overheating, because of course we should, but just to say that I'm really interested primarily in our heating-dominated climates, like the southeast of the country, with that heating loads. And here we've got a system, I think this is around 8.8 kilowatt PV system, so fairly standard size these days. Across the whole building on the right, our annual generation from the solar in the yellow bar exceeds our total consumption by about 23%. So some would say, great, I'm net positive, or whatever phrase you want to use for that. And I say not so great, because in about 4 months of the year, on the left here, you can see that our solar generation in the yellow line is well below the building demands. And the building demands in the winter, lo and behold, are dominated by the heating requirement, which is those red bars. Now, this is for the code home. So this is that house that was at 127 kilowatt hours. We've also got a bit of cooling, especially in February, that you can see there on the left. Now, how does this compare with the passive house? Well, like this. So exactly the same sized PV system, exactly the same geometry of the building, but we've taken it to passive house standard. And you can see the red bars are now comparatively tiny. The cooling bars are reduced a little bit, but not that much. On the right, we're now generating twice what the building consumes. And moreover, look in June and July, we're actually generating as much as we consume. Now, that's not to suggest that you can cut yourself off the grid, of course, because there'll still be very dark, gloomy days in June and July where you'll need to import from the grid. But you can see in terms of the whole network and the demands on the electricity grid to keep the house warm, the passive house is far more efficient and less demanding of the grid. So if I just flick that back again, the code home through to the passive house. So this, to me, is when you come to ask that question, how big a solar PV system you should get. It's not a case of getting that net zero or net positive across the year that matters. It's trying to get it positive in the most critical months of the year, which are usually midwinter. All right, let's take that same building, exactly the same geometry, and let's plonk it in Perth. This is the great thing we can do with modeling, of course. We can whack the building anywhere and see what happens. And to start with our code-built home, so 90mm timber frame, yeah, I know nobody in Perth builds with timber, but let's pretend that they do. We start with a heating demand that's about half of that from Melbourne. So we're at 127 in Melbourne, we're about 57 in Perth. And that's consistent with our understanding that Perth in winter is a lot less gloomy and miserable and cold than it is in Melbourne. We can run through this similar sorts of scenarios to work out how to optimize or improve this building. Double glazing, of course, is often is the first port of call and has a significant improvement, as does thermally broken aluminium windows, right through to high performance double glazing and so on. And you can see that this is comparatively much easier to hit a high performance standard like Passive House than it was for the Melbourne building. Again, no surprises there. But the difficult bit, of course, in Perth, more so than in Melbourne, is that you've also got the cooling demands in the summer being much greater. And so the cooling demand in the base case for Perth is actually about 51 kilowatt hours, so it's about the same as the heating demand was for the code home. Again, I can run the same scenario, and with the double glazing, I get a decent improvement in cooling demand. That's because the G value, or the solar heat gain coefficient through double glazing, is always lower than for single glazing. But really, I'm not getting a huge improvement here. And I'm still sitting, after all of those treatments around air tightness, which don't have a huge impact on cooling demand, we're at about 33 kilowatt hours of cooling demand. So we're a long way short of this notional Passive House target, which is a number of 15. So how would we redress that? Well, we just like we do for heating demand, we look at where the summer overheating is coming from. Where are all the heat gains? And the answer always is first and foremost the glazing. So the glass gets smashed with radiant solar gains, the building overheats, and we can see that here. So you've got to deal with the glass. How do you protect the glass from the radiant heat gains? We can then take a slice through our building. We've got north to the bottom left of the picture here. The black numbers are the net solar gains through the net heat gains, I should say, through the windows. So the windows to the north have got very high numbers, high amount of solar heat gain. The windows to the south have got very low numbers. Nothing surprising there. The big windows have got more solar heat gain than smaller windows. Nothing surprising there. But this provides us with some insight as to which windows we need to protect most. And so we would look straight away to say, let's take the three big ones there. There's a sliding door to the east, a sliding door to the north, and also a big window to the west. If we put an 80% block-out blind, so an external screen or blind on those windows, just as an example, we can run the model and we can work out what the impact on cooling demand was. And we're at about 33 kilowatt hours. We knock off about 5 from protecting the east window, about 5 from protecting the north, and another 2 from protecting the west. So already we've taken off a good 30% of the summer cooling demands just with 3 sets of blinds. Because blinds are expensive, we can optimize. We can actually run the scenarios and check which windows are most in need of blinds. We can play around with glass. So there's 2 parameters with glass that we talk about, the U value and the G value, or the solar heat gain coefficient. The U value is the thermal transmittance. You always want that number to be as low as possible. The G value, or solar heat gain coefficient, is a bit trickier because in the winter, in a heat-dominated climate like Melbourne, you want as much solar heat gain as you can. And that's also true of Perth or Sydney. In the summer, though, you want the opposite, and you can't tune the glass seasonally by G value. But what you can do is in the model, you can run a range of G values. So on the left here, we have very low G values. So that represents like a low E treatment of solar control glass that reflects a lot of the radiant heat back out. So it protects the building, and you would always go with that We almost always go with that in a very cooling dominated climate like a Darwin or a Cairns. In Perth, it's a bit trickier because it's a bit of both. And so if I go for a solar control glass, that helps me a lot with my cooling in the blue line here. So in fact, I'd get to the passive house standard just by specifying solar control glass, but it blows up my heating demands in winter. And so, and then on the other end of the spectrum, if I go for a glass that has high solar gains, as we would typically do in a heating dominated climate like a Hobart or wherever, then it helps me with my heating in Perth, but it's really killing me in the summer. And so I need that alternative treatment like the blinds to deal with that situation. But there might be some combination here of blinds and solar control and high solar gain glass that gets us the optimum for this particular project. And so if I go with that solar control glass, as I alluded to, I can now get myself to a passive house sort of level of performance, but at a little negative impact on the heating demand. So just 3 more slides and then I'll go quiet for a while. Once you've got the model set up, you can run lots and lots of fun scenarios. And again, this is about that trade-off between cost and performance to try and find the best combination that's going to work for your client's project. Now, here's just two other examples I'll give you here. One here is the HRV specification. So I've picked some examples, not to pick any particular examples, but just to give you an idea. One of the key performance parameters for an HRV is the heat recovery efficiency. So how much of the heat going out through the heat exchanger is recovered and re-injected back into the incoming air. And for this particular project in the Melbourne climate, a lesser performing unit on the left here might get you a heating demand of around 12.6 kilowatt hours. Whereas if you go for a very high performance unit, you could knock off about 0.7 kilowatt hours of your heating demand. So having got that number, you can then go and get your quotes from your suppliers, and you can try and trade off where the cost-benefit equation best lies. You can even look at some really nuanced things like the edge spacer in your glazing unit. And here I've got a comparison again on the heating demand down the bottom between aluminium, which is traditionally what we would have used, stainless steel, which is less conductive than aluminium, which gives us a bit of an improvement, all the way through to some quite high-end warm edge spacers. And I'm getting an improvement of around 1 kilowatt hour. Now, if we had our code-built house, you'd have to look and say, well, that's just not worth the effort because 1 out of 127 is a meaningless number. But in a passive house where we're looking for every little gain we can get, obviously that 1 could make all the difference between compliance with the passive house standard and not. The other thing, and this is obviously so topical right now, given everything that's going on, is the climate impacts. So we're designing based on a climate data set that's usually, I think the meteor norm files we use are an average of a 1981 to 2010 climate. And that's ancient history. We're in a different climate now, and we're going to be in very much different climate going forward. But what we can do in PHPP, and I assume in many of the other energy models as well, is we can try and simulate a future climate. And so what I've tried to do here is to take that historic climate data for this Melbourne dummy project and look at the impact. So now we've ran around a 0.5 degree temperature increase versus the historic values. And we can see that we're getting reduction in the heating demand of about 6%, but again, an increase in the cooling demand about 11%. And going forward, 2050, when I'm 75 or thereabouts, we're going to need about a third more cooling demand and a lot less heating demand. But perhaps more critically for the building is to consider how should I size my cooling capacity to accommodate that future climate? And the cooling capacity is shown here on the blue line at the top. So with the historic climate data, we need about a 4.7 kilowatt cooling system. This is for the passive house in the Melbourne climate. Even at 2100 with 2 degrees of global of warming, by which point I don't think the house performance matters anymore, you're talking about an extra 10% of cooling that you were going to be required. So presumably you've oversized your cooling system anyway to accommodate well more than that. So it's much less sensitive to that. All right, and with that, I'll hand it back to Hamish and hopefully have some conversation.
Awesome. Thanks, Cam. Now, if there are a couple of questions here, and it's probably quite difficult for me to kind of see if people are raising their hands or not to say yes, they're happy to to ask the question. But there has been a couple of questions that have come up now. One of them was from Michael Longton, and he basically just said, so PHPP can work even when you don't have an internal air barrier. Maybe if you just want to talk to that quickly, Cam, just about how you can model in different air changes for when you are doing the modeling in PHPP.
Yeah, so PHPP doesn't explicitly require you to specify anything about an internal air barrier. You could conceivably use plasterboard as your internal air barrier. It's all you're doing is entering an air change rate. And then for the purposes of certification at the end, if you're going for the passive house standard, then you have to get the building tested, blower door tested, in accordance with the standard, and then that number will then be updated back into the model.
Now there's a great question here from Michael Norris, and it's a topical question that comes up with us all the time, and it's got to do with what air change should we be putting an HRV in. So Michael has asked, will 5 ACH require an HRV unit?
So this keeps coming up, and 5 is the number that everybody talks about. Firstly, there's no threshold between when a mechanical ventilation is required versus not. Secondly, I would argue that all buildings that do not have mechanical ventilation have far inferior air quality to those that do. So if you value indoor air quality in your building, and who doesn't, then you should have mechanical ventilation. I think the evidence is definitive on that. Even in a building that is very air leaky, either designed that way or maybe is from 150-year-old weatherboard that might be running at 30 ACH, maybe even worse, that building does not have good indoor air quality all the time because it's so reliant on the weather conditions outside, the wind blowing, the temperature difference driving convective air movement, and the occupants opening their windows. And even if you go to bed and think, well, I'm a sort of person who likes having my window cranked open at night, you go to bed and it's blowing windy when you go to bed, and that might be ensuring good indoor air quality when you go to bed. But what if the wind stops blowing at 2 o'clock in the morning? You have no control. Whereas the mechanical ventilation gives you a constant, predictable, climate-independent flow of fresh air into the building. So my flippant answer to that question is there's no ACH limit because you always need mechanical ventilation. But certainly at around 5 or below, it becomes more critical. Sorry, Hamish.
You go, Ken.
I'm just going to add that the other part of this is the heat recovery efficiency. So you want to maximize the in air escaping the building, you want to capture as much of that air as you can through the mechanical ventilation system so that you have the opportunity to recoup or recover the heat and then put it back into the building. So the tighter you can be, the better the heat recovery efficiency, or the better the efficiency of the mechanical ventilation system will be.
So we've actually done a webinar with Joel Seagren from Fantech on ventilation, and he echoes those sentiments. So basically, mechanical ventilation is for any home, but I guess we all kind of talk about that magical number of 5. This might actually be a bit of a tongue-in-cheek question from Luke Middleton, but he was asking who designed that building, Cameron.
I think Luke Middleton knows the answer to that question.
So this is from Miriam. Can you model different glass to different facades? Example, in Perth, allow solar gain to the north, but not the east and west.
Yeah, so that's a great question. And the answer is in PHPP, yes, you can. So each glaze unit, you can specify different glass to if you want. And so, yeah, in theory, it can be done. I can't recall actually it ever happening in a practical project, just because it just makes it a bit more difficult to specify everything and make sure that's what's getting delivered to site. But yes, you can. Often we would find, though, that particularly in a climate like Perth or Sydney or anywhere north of that, where the cooling demands are the critical design parameter, that you're still going to need some form of external shading. Particularly just around that middle band of the country where you've also still got a heating demand. So you don't want to just go solar control glass everywhere, but rather you perhaps want it on some windows and not others. But those windows that you want it on for the summer overheating are probably also those that are giving you most of the winter heating gains. And of course, by going for that solar control glass, you're precluding that solar radiation getting in the winter when you do want it. You can't tune it. Whereas a great thing with external blinds or pergolas or retractable awnings of whatever form is that you can extend and retract them seasonally.
The answer. This is from Gaz King. Jeremy Spencer has a calculation for eave sizes to enable good solar access and shading when required, and also design proposals to ensure the right windows are on the right elevations. Even in a changing climate, would this sort out any glazing issues, with the exception of the sliding doors, which obviously have to reach the ground?
Yeah, so just perhaps to tackle the eaves part of that. Yes, so in the passive house workflow, we would usually start in SketchUp, which everyone probably knows is a sort of a simple CAD package, and we calculate shading parameters there. So we would put our eaves in, say at 600 mil, we would calculate a shading coefficient, and then we would use that in the PHPP to work out what the heating and cooling demands on our building would be. And then we can run scenarios where we could extend that eave another 200 mil, or retract it, or raise its height, change its pitch, whatever it may be, to suit the architectural and client requirements to work out what the impacts would be and find something that's going to work for that project. So pretty much, I think what you've described that Jeremy's doing there.
This is actually a really good point from Paul. And it probably goes back to something we were chatting before with Michael about not having an internal air barrier. He has said you also need to consider your roof and wall build-up if you are not installing an airtight membrane/layer. A woofie is recommended once your building is below circa 5 ACH. Are you in agreement with that one, Cam?
Yeah, except for perhaps the 5 ACH number again. It's sort of a number we plucked from the sky. So in this presentation, I was just talking about the energy modeling of a whole building. The other two sort of standard things we would often do are the thermal bridge calculation. So Flixotherm, HT Flux, whatever you want to use, that deal with all those details like the slab wall junction and where you've got steel penetrating the thermal envelope. And then the third one is the hygrothermal modeling, so the moisture and the thermal, which is the woofie calculation. So yes, if you aren't going for an internal vapor control barrier in a heating dominated climate like the southeast of Australia, you probably ought to consider doing a woofie analysis to make sure you're not going to get any moisture issues. What I would though also say is that air change rate is very important in those woofie calculations. So for anyone that's done woofie, you'll find that those air change assumptions are a really critical parameter. And as soon as you put in 0.3 ACH, which is what you're achieving with a mechanical ventilation system, a lot of these moisture issues, not all of them, will tend to go away, or they'll certainly be far less critical than they are without the mechanical ventilation system, because the mechanical ventilation system is really a moisture management tool as well. And so the way I try and think about that, if you compare a bathroom where you have your $20 extraction fan that runs for 10 minutes when you have a shower, it blows away, taking out 25 liters a second, but then it turns off after 10 minutes and the tiles are still wet. And so all that moisture then builds up, floats around in random, unpredictable ways through your building. Whereas with the mechanical ventilation system, you're constantly extracting that moisture and thereby reducing the risks of condensation in your assemblies.
Very good point. This is from Luke Middleton again. What's your opinion on the cross ventilation heat purge input within PHPP versus actual results in the Melbourne climate?
Yeah, great question, Luke. Whether it be the Melbourne climate or any other climate, the way the summer ventilation works in PHPP, and no doubt in many of the other packages as well, is it requires a deal of assumptions about how often the occupant opens windows to start with, which I think is really problematic. And one of the stress tests that we're encouraged to do in Passive House is to assume in some of the client does not open windows. The problem is that in almost any Australian climate zone, when you make that assumption in PHPP, you've got no hope with the summer overheating. And so we are reliant on the occupant being sensible. And when the cool change comes through in Perth in the January and the Freo doctor comes through in the afternoon, that you open up to purge the building. There are other factors in there like the stack effect. You get a much better ventilation throughput in the PHPP if you open a ground floor window in combination with a first floor window. But there's nothing that accounts for the presence of internal windows. And if the occupants keep internal doors closed, there's not going to be the coupling between those windows anyway. So I think it's a very difficult thing to model.
Okay, I do have another couple of questions here, which I did answer earlier on. Michael has been quite active, and I'll just read this out. Hey there, I'm just wondering if I should approach someone who does PHPP modeling if building a high-performance building. I know NatHERS doesn't account for air tightness, so are there other energy consultants that can assist, or just someone in PHPP? He's just talking about quite a specific build-up here. So looking at airtight, external vapor permeable membrane, 140 studs, R4s, below slab and slatted insulation, tilt-turn windows, airtight plasterboard and HRV.
So yes, I think is the answer. Modeling always makes sense no matter what you're trying to do. We come back to that argument about it depends. And I just make this sort of observation about Passive House. There's a lot of the thresholds that we use, like this magic number of 15 kilowatt hours for our heating and cooling demands, is in a sense arbitrary. It's a standard. You need to have a threshold. There's nothing magic about hitting 15. And for a particular project where you're not interested in Passive House and you're going to be quite comfortable with something in the 20s sort of range or whatever it may be, fine. But I would still argue it needs to be modeled, whether that is in PHPP or anything else. It doesn't have to be a Passive House project to model it in PHPP, just to get a feel for what's the right combination of insulation in this part of the construction versus that, the glazing that we've talked about, and so on, to find that cost optimum path that has a good chance of getting you what you hope and anticipate out of your building.
I can talk to this on a particular project we're working through with Cameron at the moment, where we're looking at different wall build-ups, different window suites, different slab insulation, and the impacts on different wall build-ups and windows on performance, but also allows us to look at the impact on cost as well. And this particular project could get to Passive House standards, but it's not the goal for the client. Well, it's not paramount that we get there. We're just providing all the information to the client so they can actually make considered decisions based on performance and cost. We understand at Sanctum Homes that This is a pretty tricky time to be building homes, particularly higher performing homes, which do cost a little bit more to build. So we just want to be able to give options, and modeling in pre-construction, we think, is a really cost-effective way of doing that to kind of test those different factors. I've got another question here from LJ Cam. Are there any trends slash patterns you've seen across climates? They are interested in Perth in particular, which suggests particular things present greatest bang for buck for performance. They're trying to build an appropriately performing low energy home with low embodied energy materials and unsure which components will achieve the right cost benefit for our project. It probably touches on what I was just explaining before, Cam, but I'll throw it back over to you.
Yeah, probably going back to my first slide really and say it depends. What's the building look like? Is the orientation to the south with all glass to the south? That will change things versus other orientations. Perth's actually but to talk generics, because that was the question. Perth's actually a really difficult climate, I find, because it still has reasonable heating demands, but it also has high cooling demands versus your Canberras and your Melbournes. And that makes it much trickier, particularly the question around, say, the thermal decoupling of the slab, because in the summer it's helpful. It can be somewhat helpful to have a slab to ground in those sort of cooling dominated climates, but in winter it's detrimental. So you do tend to come back on, really rely on those variable external shading devices like the blinds to manage your cooling in the summer, while trying to optimize for your winter heating demand. And I'd also just come back to, again, depending on what you're trying to achieve, of disproportionately weighing the winter heating demand, because you have your own solar generation to meet that heating demand, whereas in the summer, you will have plenty of excess PV available to run your AC on that February afternoon. If you want to whack it on for a couple of hours, it's relatively guilt-free in the sense that that you're at least generating it off your own home and it's carbon neutral. Now, that's not to say we should ignore summer cooling, of course, but just that, to me, it's that midwinter issue that's the critical one.
We seem to have a lot of people from Perth here tonight, Cameron. Maybe Brian is drumming up some people over there. This is again from Miriam, and again talking about Perth. Could it be that as long as you get sun on that thermally decoupled slab in the winter, you can get heat, or is that not equivalent to being connected to the earth?
So this comes to this perennial question of thermal mass, which is highly debated. So again, acknowledging that I come from the passive house side of the world, the passive house consensus view, I think, is that thermal mass can be somewhat beneficial, but it can also be detrimental, and that it's not necessary if you get all of the other elements of the thermal envelope right. In effect, the fact that you've got all of that continuous insulation and that fantastic air tightness, your whole building is operating as thermal mass. Having said that, yes, there can be some benefit of having a thermal mass that sort of acts like a battery in the winter, but you've got to consider where that heat's transferring to. If that's a thermally decoupled slab, yeah, you can get the heat back. But of course, in the summer, what do you do then? And so we're back to those external blinds. And just as an anecdote, is not data, as per my first quote here, but in my home in Melbourne, I've got a rammed earth wall, and in the summer, that's quite beneficial on the first 2 or 3 days of a really hot cycle, whereas it's effectively absorbing that heat. But then, of course, when the cool change comes through, it's then re-radiating that heat back into the room for the subsequent 2 or 3 days when it's cooler. So it's really just moving the heat problem, delaying it by a few days. So it's not it's helping me somewhat in the summer, but probably not as much as one might think or hope. And conversely, in the winter, I would argue, as long as you've got that radiant heat coming in through the glass, then it will heat the air and the sofa and all of those other objects in the building. and as long as the envelope is nice and tight, it will retain that heat without the need for the slab. And sorry, and just to add to that, we've got to get away from building with concrete and foams and all of these carbon-intensive, unrecyclable products. So, and hence I'm a lightweight floor kind of guy.
So, I mean, just on thermal mass, Jeremy's done a whole bunch of really great posts on the Builders Declare Instagram page on thermal mass. And just for clarity, we're not just all about passive house here at Builders Declare. However we get to building low energy, sustainable, high performing homes, we're all about that. This particular presentation and PHPP is, I guess, focused on passive house and high performance homes are following those principles. There is one more question from Jeremy himself, which will probably end on. He has said, PHP, can you ask Cam how PHPP can be used under the NCC performance solution outside New South Wales?
I think the short answer is at the moment is that it can't. It is great now that we can use it through basics in New South Wales. Unfortunately, outside of that, we're still having to do for a passive house project, we're still having to do the PHPP and then separately engage an ATES consultant to do the energy rating to get compliance, which is obviously feels rather unnecessary and duplicated, but that's just how we are at the moment.
All right, Cam, we're just over 6 o'clock, so I think it's probably a good time to wrap it up unless anyone's got any other questions. Cameron, thank you so much for coming on today. As someone who works in the passive house space, I genuinely appreciate the work that you do. There has been a couple of questions about getting in contact with you if they can. Would you mind sharing your contact details for the people here?
Yep, sure. I'll just put up. Let me just put the front page up. I think I'll put my email address there. There you go. I think it's my email address at the bottom.
Perfect. As I said, we've got a couple of projects with Cameron on the go at the moment, and it is incredibly beneficial. All right, I'll wrap things up. Thank you, everyone, for joining us tonight. Definitely don't forget to listen to episode 20, part 1 and part 2 of our podcast, Sustainable Builders Yak, where Simon and Brian catch up with all the 5 members of Builders Declare and soon to be Sustainable Builders Alliance. You'll get the opportunity to get to know all 7 founding members of Sustainable Builders Alliance and our motivations to get involved with Builders Declare in the first place. We also touch on what the future looks like for SBA, which is Sustainable Builders Alliance. Check it out on Spotify, Apple, or wherever you listen to your podcasts. Now, next webinar is a really exciting one, and I can actually thank Cameron for reminding me that such a product exists. We're going to be joined by Ryan Stratting from Core Collective and director of Clinker. And I'm holding here some expanded clay. It's basically like popcorn clay, and it can be used for sub-slab insulation. And I guess referring to what Cameron was saying before about removing foams and all that kind of stuff from our buildings, we're hoping to use this particular project and this particular product in an upcoming project to remove some of the XPS. Now, I'm not saying XPS doesn't have its place, but I'm also excited about the opportunity to use this. So I'm actually catching up with Ryan tomorrow, so we'll be locking in a date for that later on in August. And lastly, stay tuned over the coming weeks as we are going to announce the date for our launch event for the new website and the new brand for Sustainable Builders Alliance. There is going to be limited tickets for this, and it's going to be in Melbourne and Collingwood at Stomping Ground. Thank you all again for joining us today. And I will be getting this up on YouTube over the next couple of days for you to rewatch because there's a whole bunch of really amazing information in there. If you want to get in contact, info@buildersdeclare.com, and you can join in the conversation on Facebook and Instagram. Thanks, everybody. And Cameron, thank you so much for the fantastic presentation. See you later.